good talk. So today we're going to finish up our, I guess, naive or basic sorting algorithms by going over selection sort and insertion sort. So your lab will be to finish implementing selection and insertion for an array base. Yes. And then you can pick any of the three we've gone over, bubble, selection, or insertion, and you want to implement that for a linked list.
Is that for lab 11?
Is that what lab we're on, 11? Whatever the next,
Yeah,
oh, 12.
Well, because you assigned lab 11, but it's not up on GitHub yet.
Oh, that's cute. All right, well, I'll make sure I push that.
Yeah, because I was trying to look at it.
Well, I'll assign lab 12 today.
So you don't have to.
Oh, I will. Oh, I will. All right, so selection sort.
We're already up to the amount of labs we were in Java.
Dang.
No, I think we've surpassed it. There were only 10. There were 10.
We're not even like halfway through, and we surpassed Java.
Yep.
So.
Just how it rolls. All right. So selection sort, this one is probably a little more intuitive because it's probably how a lot of y'all do sorting if you had a bunch of stuff. Basically, you look at your list and you find the smallest one, put that at the bottom. Then you look at your list, find the next smallest one, put that next. Then look at your list, find the next smallest one, and put it on your list. Does that make sense? Yeah. Or you could do it with largest if you preferred. You can also do this with linked lists because you can just keep a pointer to the tail and keep adding the next smallest one to tail. Okay. Wow, they don't even give you pictures of selection sort? Oh, that's terrible. All right. So the
That just means you need to draw a picture.
All right, well, let's draw a picture. I don't know if you realize this actually can hurt you if you make me do too much work on the board, but that's okay. All right, so give me a list of numbers.
1, 2, 5, 7, 9, 63, 44.
Okay, first off, this marker's terrible.
Yeah, you didn't see it.
Oh, terrible.
Had that board out.
That goes to basketball.
Now it's a good thing, unless it was yesterday
What?
in Java, and I totally nailed it.
You nailed it.
Oh yeah. All right, let's try this again. All right, give me a list of numbers not sorted whatsoever.
5.
8, 6, 12, 44, 15, 31,
2.
2, 8.
2. All right, we're done. All right, so there's two ways to do it. You can do it from smallest to largest.
That's kind of how you drew them.
Yes.
Largest, smallest.
It was, right? Yeah.
Yeah,
How's that? Okay, it's coming out well.
as long as you're gonna space.
That one doesn't erase.
So step 1, you find the smallest one, which is a
2.
2. All right. Then you find the next smallest one, which is a 5.
Oh, 5, yeah.
Okay.
Jeez.
Then you find the next smallest one, which is a
6.
all right. Then you find the next smallest one.
8.
All right. Then you find the next smallest one. 12. All right. Am I off the board yet? Not yet. Okay. So we'll go dot 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 2, 5, 6, 8, 12,
15, 44.
15, 44. Okay. So the question is, how long does this iteration take?
1 half.
O of,
Oh, 1.
why would it be O of what? Yeah,
N times because
you have to go through the whole array.
yeah.
Now the second time you look through it, do you have to go through n times?
N minus 1.
N minus 1, and then
minus 2.
all the way down to 1. So on average, you're going about half of n, right?
Yeah.
Okay.
So it'd be M.
So
plus N
each
plus-
iteration is O of n. And how many iterations do you have?
However many. Oh, it ended up being N squared.
Yep, because now you have n iterations that you have to go n times, so we're still n squared. Now, that is for comparisons, right?
Yes.
How about for swaps? Now, I didn't exactly write this out completely. So let me back up and show you what's actually going on. Here at this point, the array, you just swap the 2 and the 5. So you'd have 2, 8, 6, 12, 44, 15, 5. And then here you go 2, and so you'd swap the 5 and the 8. So you'd have 6, 12, 44, 15, 8. And then
Hey, 6 stays the same?
Oh, hey, it would end up sorting it. Oh, that's cool.
6 stays the same, right?
yeah, so 6 is in its place, so you don't have to sort anything. Well, that was handy.
Right?
Yeah. Now you have to swap the 12 and the 8. So that's
44.
hold on. Yeah, brain stopped for a moment. Now kick back up. 12, and now you have to swap the 44 and the 12.
And it sorts the last one out.
All right. So how many swaps, worst case, did you have to do per iteration? One swap, okay? So there's only one swap per iteration, and there's n iteration, so it's O of, right, so your swaps are O of n, but your comparisons are O of n squared. Okay? How is that different than bubble sort? How many comparisons were in bubble sort?
No. Well, it was an O of M operation.
Oh,
N plus 1 divided by 2?
Well, the base 2 then.
I feel like we're throwing darts at a board. All right.
We can get a dartboard.
Wee! Hi. Okay.
Oh,
That was only 2 days.
5.
Put Dr. Underwood's face at the center.
Now, where's
I know.
sorting? So bubble sort, if you recall, you start at the bottom and you compare the two. If the first one's greater than the next one, you swapped it, and then you compare it again to swap, so it bubbled up. Okay? So how many? Let's see. Did I put this somewhere? I probably put it in searching. I bet is what I did. Called it linear search. Yeah, I would do that.
Yeah.
Keep forgetting to do this.
Really need
I really do. One more time. All right. So how many comparisons are there?
to. Oh, but
N squared.
Y n squared.
because you have to do the outside and then you have to do
It's a mess.
How many swaps are there?
As many as like go half the amount,
half of it.
half a
Seven.
Never mind.
What have I done?
It's roughly O of N.
All right, hold on. I don't know what just happened.
I don't know either.
How many times is this line executed?
I.
O of
Oh, never mind.
O N squared.
n squared. Why is it O of n squared?
2 for loops.
Yeah.
Any questions?
No.
All right. How about this line?
No, that's all one.
Oh.
How many times is it executed?
N squared.
N squared.
N
How many
squared.
times? Okay. So
Bubble sort.
these three are swap. This is comparison. So where comparisons are O of n squared and swaps are n squared as well. All right?
So
Bubble
the
sort
new
better.
one is slightly better for the swap, but the same. The
Right. So this one is better, is the same for comparisons. You're still doing n squared comparisons, but you're doing just O of n swaps.
So this one better.
So this one better. All right.
Slightly. It's not over, but it's better.
We need sorting done in O of 1.
That ain't happening.
That ain't
Next
happening.
table sound fun.
Stop.
It's still at least, that doesn't even make sense.
I think on it. It's okay.
All right. Function swap, just 3 assignments, execute n minus 1 time, so it's O of n. And let's see, find midlook. Wow, they're just throwing up functions here. So find the min location, aka that operation we did each time to find the minimum value. It's done key -1 comparisons, executed n -1 times, so aka it's n squared. Yes?
She asked if I got legit coffee because I was writing on it, and I was like, no, I took her pen and wrote on it.
That's why you never go and get the big coffee.
All right, so that's selection sort. Are there any questions about selection sort? No.
Next.
All right, insertion sort. Good, that was half the sorting algorithms for today.
Yay. Whoa.
That was nice.
Yeah, it is fast. All right, so we'll take this.
Oh, why'd you take the 2 away?
I'm putting it back. All right. I was just erasing the board for those of you online. So sorts a list by moving each element to its proper place in the sorted portion of a list. Ooh, are we going to get examples? Oh, we are. Okay.
Everyone seems down today.
Hmm?
Is it just me or everyone seems down today?
I don't know what.
Everyone's happy, man.
Well, you're smiling
Playing
now.
with the green tissue.
All right. So the idea is that you're going to build the list and maintain it correctly. So if you had this list where it was 10, 18, 25, 30, and you need to move the 23 in the correct location of these 4 numbers, where would it go?
2.
Right, to the 2, thus shifting the 25 and 30 down. So you create a temp copy, copy all those guys over, and then you move the 23 in, and you're done. Okay?
Wait, can you go back one? Yeah.
Let's do it on the board. On the board. All right. So we want to find the correct list of 1. Obviously, that's just going to be the minimum, which is the 2. All right. So it's 2, and then we're going to shift everything down. 2 is at the end, so we have 2, 5, 8, 6, 12, 44, 15. All right. I did that completely wrong. Let me start over.
Okay.
I just got the 2 sorts confused. So erase everything I just said. We start with the 5. The 5's in the correct place, right? So we don't need to do anything there. So we look at the 8. Do we need to move with 5 and 8? Is that already sorted?
Yes.
All right, so we're going to leave that alone. 5, 8, 6, 12, 44, 15, and 2. All right, now we're going to look at the 6. Do we need to move that somewhere?
Yes.
So we need to move it basically between the 5 and the 8. So now we have 5, 6, 8, 12, 44, 15, 2. Now we look at the 12. Do we need to do anything?
Nope.
Wow, someone really gave me some nicely already sorted elements. 12, 44, 15, 2. We look at the 44. Do we need to do anything?
Nope.
All right, 5, 6, 8, 12, 44, 15, and 2. Good. All right, now we look at the 15. Do we need to move that?
Yes.
Where do we need to move it?
Right before.
All right, so we got 5, 6, 8, 12, 15, 44.
Bless you, bless you.
2.
2. All right, then we look at the 2. Do we need to move that somewhere?
Yes.
Where?
The very beginning.
The beginning. All right, 2, 5, 6, 8, 12, 15, 44. All right.
Now how do we code this?
Huh?
Now how do we code this?
Well, let's do a big O analysis of it, though.
Oh, then.
At least think.
So that means it's wrong.
Why is it wrong?
So, how many comparisons are there per iteration?
1.
Oh no, there's a lot. What I'm
There's a
saying?
lot.
Because you have to compare.
And-
If you're trying to shift it, you have to compare it to each variable until you figure out if it's less than one of them and put it in front of that. So it's a lot of
almost sort of
comparisons.
end.
So bad.
Yeah, so for each iteration, it's about O of n. And how many iterations do we have?
And
N. So comparisons is still n squared.
still not good.
All right, how about shifts? Shifting. Shifting.
Still
It's still.
Per iteration, how many are there?
2. No, 1.
I mean, you're only shifting one thing, but.
Well, how many
why
times
is
do we
he
have to
saving
shift
it?
here?
0. Oh,
You have to
shift
Oh,
so if we get 2 to the front,
Yeah,
you have to shift everything down.
everything. So that was O of
And
n. And how many iterations is it?
And
So it's
really
And
bad.
squared.
Don't do this.
Don't use this one. Bad.
Never mind, we don't need to have
Do
know how to
something
code.
efficient.
We don't do that.
Works hard.
It's not useful, don't need it.
That's what she said, not me.
Put a sword.
all right. Now hold on a second here.
Merge sword.
Let's think about this for a moment. Compare n squared. All right. Let's think now. This is for an array. How about for a linked list?
It would be a lot better.
Is comparison still n squared?
Yeah.
How about shifting?
And
Yeah, now it's O of n.
So we only need to know how to do it for a link list.
No.
for that comment, put it on the test.
Is there any of these algorithms that can make the linked list sorting O of 1?
You can't do a sort of one.
Yeah, I
N
know a
would be the
spell that
lowest.
does that.
No, it doesn't really. I'm not familiar with any. I'm sorry, no comparison-based ones. So, that's hard to see.
Just read it.
But we went through the array. No matter what, you had the comparisons were O of n squared. But shifting, you could do it with an array. It's O of n squared because you have to shift everything down. With a linked list, it's O of n because you just put it in the place and you're done. All right.
Yeah. Sure.
Ah.
Alright.
All right. Let's do some other fun analysis. Wow, this is gonna be a short class today.
Are we gonna
Are we gonna code it?
We're doing lab, are we gonna code anything?
Yeah, we're gonna code.
Who needs who needs to know how to
That's your job. No, we'll get to it in one moment.
Okay.
The for loop executes n minus 1 times. Best case, the list is already sorted. Key comparison is just O of n because you're done. Worst case for each iteration, the if statement evaluates the true, so your key comparisons are back to n squared, like we said up there. Average number of key comparisons, therefore, only came up with this formula. It's still O of n squared. All right, let's go compare them all. Bubble sort, comparisons n squared, swaps n squared. Selection sort n squared, swaps O of n. Ooh, that's better. Insertion sort, comparisons n squared, and swaps O of n squared. Does this make sense to y'all?
Yeah. They all kinda suck.
Yeah, basically.
Wow.
We still learn them.
They're not the greatest.
What are we doing? Oh, we're not doing binary trees.
No, thank you.
But why?
We're not doing it right now. Oh, we haven't got a quick sort. Wow, that was it for today? Man, we're doing awesome.
Nice.
Okay.
Cloud time.
Gotta learn how to code it first.
All right, so that's all for the lecture. You.
Oh jeez.